Okay.
Let's click on got it. Then.
Got it.
Okay. So welcome everybody to this Laws of Nature seminar. I'm very happy to announce our speaker of today, Daniel Sudarsky. He came here from Mexico. He's a professor for theoretical physics at UNAM, University of Mexico. And his research is focused mainly on the interface between quantum theory and general relativity. So he will speak about this today, mostly about spontaneous collapse theories in the context of general relativity. So thank you, please.
Okay, thank you. Thank you for the hospitality and for being interested in this subject. Okay, I will try to give a relatively short overview of the work we have been doing for now over 15 years with a relatively long list of collaborators. So I will not be naming everybody that has worked in every single aspect of the story, but in general, people have, contribute dramatically in different ways to this enterprise. Okay, so, oops, now we have a problem of control.
Maybe.
Mm-hmm.
I think we can first hide the upper bound here by saying the more, and the height. I think the floating meeting controls.
Okay.
Yeah, and I think this we can. I think you can make small.
Okay. And now. Oh, okay.
Okay. So we're
good.
Now showing a different name who's talking, but it's my computer.
Okay.
but
that's okay.
Yeah.
That's okay. Okay, so I will briefly describe the measurement problem in the gravitational context, starting by reminding you some aspects of the measurement problem, but indicating why I think it becomes more serious in this situation. And then I will explain how we plan to explore this gravity quantum interface without necessarily trying to do quantum gravity. Our posture regarding quantum gravity is, of course, it's likely that we need a quantum gravity theory, but at the moment despite great efforts by many in many programs, we don't really have a working theory of quantum gravity. And then I will, after describing our general approach to this issue, I will start with the applications. And the applications that on which I will focus today are those that have to do with inflationary cosmology, in particular the account of the emergence of the seeds of structure, the data that we can see in the CMB, and then another couple of aspects of the theory where, in contrast with the first, we will see that our approach produces rather different answers than the ordinary ones. And then I will make some final considerations and mention other regimes where we think the theory can be, or the approach can be very useful. Okay, so the first thing to accept and to realize is that to think about physics without a space-time framework is a very difficult one. I have tried it, never succeeded. And if you at the same time want to adopt a relatively clear and definite view about quantum theory, then things become even harder. One of the drawbacks of not adopting a specific clear posture in this regard is that one is often led to confusions. And one of the places where confusions arise very often is in connection with the word fluctuations. This is a word, unfortunately, the same word is used in very different situations. For instance, we talk about fluctuations if we are considering some extended system and we want to talk about some aspects of the system and they are changing either in position or in time. For instance, the surface of the water is changing. We say it's a fluctuating thing. Then we could have, a variation of a definite quantity within an ensemble of systems, of separated systems. For instance, well, here is one example, but you can think of the grades of students in a class. You have a collection of systems. There are, an ensemble of systems. Each one of them has a definite value of the quantity, but, you could say, okay, there are fluctuations in the grades in my class or something like that. Of course, in physics, we have plenty of examples. And then we have quantum indeterminacies or uncertainties in a single system. And we also talk about those in terms of the word fluctuations. For example, fluctuations in the position of the harmonic oscillator in its ground state. Those words we use to define, to represent, for instance, the uncertainty in the position or the momentum in that particular state. And failures to distinguish between these are very problematic. They are often connected to failures to distinguish between proper and improper mixtures. I remind you, a proper mixture is normally we describe in terms of a density matrix, but it's clear that what we are doing is providing a condensed description of a large collection of systems by a single object. In that case, there are definite probabilities for the system or definite frequencies in which systems with certain values of the quantities appear, or different states of the system appear. So we have a collection of harmonic oscillators. They are all in definite states, but in different states, and we may describe that by a density matrix. So it's a condensed description, but of something that we could have described in other ways. For instance, we could have listed all the states of all the elements of the ensemble. A very different type of mixture occurs when we have an extended system and we decide to ignore a certain number of degrees of freedom, and then we trace over those degrees of freedom, and then what we have is called an improper mixture. We still have a density matrix, the same looking mathematical object, but representing something completely different physics-wise. And we should keep this in mind, this distinction, to avoid confusion. Okay, these type of confusions are kind of dangerous. One example where we can see the danger appears in a very popular approach that's called stochastic gravity. It's not that I want to say bad things about stochastic gravity. Actually, they face a problem that we will face as well. But here the problem is that the problem cannot be easily recognized. The problem is basically the following. They write Einstein's equations for sources that are quantum mechanical. So we equate the Einstein tensor to the expectation value of the energy momentum tensor. And then one is told that this doesn't account for the fact that there are fluctuations. And then to represent the fluctuations, one adds this term, which is in fact a stochastic variable for which one requires certain statistical features. And it's easy to see that the ensemble average, by the construction of this object, the ensemble average of all the realizations satisfies that equation. The ensemble average of the divergence of the stochastic fluctuations vanishes, but it does not mean that each individual element of the ensemble vanish. And when we're doing averages, here, what we would be doing is writing equations that are inconsistent, because this guy in each individual case doesn't have a, the equation is inconsistent. The right-hand side has automatic zero divergence. This object has automatic zero divergence, and the last one will not have zero divergence in each one of the instances of the ensemble. And so we will have a collection of inconsistent equations, and we somehow would hope that by averaging, we would obtain something consistent. That is not very clear why we should have that hope. Okay, and all these kinds of things that I have been mentioning can be traced to a tendency of ignore or try to avoid facing the M problem. And I decided to give it the M problem because it has become very popular to name big things by the M problem. And here we have the M problem, the elephant in the room, the thing that nobody wants to talk about, but everybody knows is there. So we need to face the measurement problem. We will do so in a particular approach. But on top of that, we want to explore the gravity quantum theory interface. And we will do that in what we call the top-bottom approach. The usual approach we describe as the bottom-up approach. I don't know if this is which direction is each, but okay, I have taken this particular convention. And the bottom-up approach, I imagine at the bottom, the more fundamental, the more, the thing that you believe is closer to a full description of the real world. And the bottom-up approach starts by postulating or taking for given that you have in your hands the fundamental theory of gravity. And that's what our colleagues in string theory, loop quantum gravity, causal sets, dynamical triangulations do. They take a theory, they accept they have in their hands this fundamental theory, and then they work very hard to try to connect with the world out there, the world where there are black holes, cosmology, etc. The approach we will follow takes the opposite direction, is rather agnostic regarding what is the fundamental theory of gravity, but says we have certain, or what's the fundamental theory, period. We have certain well-tested and theories we have very good reasons to trust. And of course, they don't extend to all the domains we would like them to extend, but we will here push them to try to extend their application beyond the normal domains and see where is this domain, what happens in this extended domain, and when they will start to clash, and see what can you do about the clashing. The idea is to look for relatively small modifications that could serve as clues to a nature of a more fundamental theory. So if everything went fantastically well, the two approaches would meet in the middle. But okay. So here, concretely speaking, I'm talking about taking our best theory of gravitation, which is GR, taking our best description of matter, which is quantum field theory, in particular quantum field theory in curved spacetime, and putting them together and trying to explore with that some questions that are usually not explored in that sense. Moreover, we will try to take a relatively definite view regarding quantum mechanics, or in particular an ontology, and definite ontology. And since this approach calls for describing spacetime in classical terms, something that we expect to be reasonable if we are far away from, let's say, Planck scale curvatures, and the quantum uncertainties are not too large. And I left it like that because it's not exactly clear what we mean by that. We believe there should be regimes in which this should be okay, and matter should be treated quantum mechanically. So it seems natural to say, to take a posture even if it's a provisional ontological posture, to say that what the local variables at point X are what determines how space-time is curved at point X, and that is the expectation value of the energy momentum tensor, or whatever you put in the right-hand side of Einstein's equation should. Of course, there is a difficulty, which I already mentioned in the context of stochastic gravity, that it appears that all possibly satisfactory approaches to dealing with the measurement problem in quantum theory leads to expect violations of the conservation of the expectation value, or whatever you put, you end up representing your expectation, your energy momentum tensor. So we wrote a paper about that. If you want to see all the details, you can look at that. So whatever we do, this is something we will have to deal with. The reason we call this thing provisional is because we, of course, expect something dramatic to occur when you really leave this regime and go to a regime where where a full quantum gravity theory is required, something we will try to do not. So regarding the measurement problem, we will focus on, as mentioned by Paula, on the spontaneous collapse theories. And well, if you probably here in this audience, you'll know that collapse theories have a long history. There is a large amount of work by lots of people, from Girardi, Rimini, Weber, Phil Pearl, Lajos, Diossi, Roger Penrose, and more recently, Bassi, who is one of the organizers of Angelo Bassi, who is one of the organizers of this thing. And there are some proposals, some more recent proposals, to make the theory compatible with relativity. I will not get into any of those. In fact, I will try, for the most part, to say things that are rather general. The basic idea of these collapse theories is to unify the two types of evolution processes that appear in textbooks of quantum mechanics, the unitary evolution and the reduction process. And the idea is that this would produce changes. The theories are designed so that they produce changes that are very small when we have very few degrees of freedom involved, and become very large when something like Avogadro's number of degrees of freedom make their appearance. These theories address the measurement problem in a successful way. Some of them have been subjected to serious constraint, and there is some versions that even have been claimed to be ruled out, but that's not the point. In the relativistic regime, we do have then theories that seem very, in the non-relativistic regime, we have theories that seem reasonable. And as noted, in our context, we will use an ontology that is based on this object, the energy momentum expectation value, which should not be regarded as an average, but more like the relativistic version of, let's say, the mass density of, let's say, MGRW approach, where you take the mass density to be the actual, provide you with an ontology. Okay, so this seems very natural. Okay, the theory which underlies the calculations that I will show you has, for the most of the part, been this continuous spontaneous localization theory. If you haven't met the equation here, I introduced to you, is an equation that is a modified theory whose better, it's easier to write the solution than to write the equation itself. The solution, the evolution of a state. Do I have something to point?
Not really.
Okay, so anyway, so you see that the first part of the evolution, it represents the standard Schrodinger evolution of a system. And then you have corrections that involve various elements. The elements that we see appearing there as extra elements or as providing the modification are basically three elements. One is the, thank you. One is the strength of this modification characterized by the parameter lambda. Another one is a stochastic function of time in the case of a 1 degree of freedom, a system with 1 degree of freedom. And then an operator that tells you towards which type of states does the theory tend to drive an arbitrary initial state. In this case, it would tend to drive the state towards eigenstates of the operator A. And we call this operator making this appearing there, we call it the collapse operator. Okay. Second, since the evolution obviously is not unitary, you have to change the way you use the theory. In this theory, instead of computing amplitudes in order to compute probabilities, you compute probabilities for realization of each particular stochastic function of time in between any two times, and the expression is here. Okay. This dynamics is designed, as I said, to unify the unitary evolution, and in this case, the reduction process corresponding to the observable A. So this is the observable that will play the object that will play a fundamental or a privileged position in the theory. That's taken to be, in the non-relativistic cases, is taken to be something like a smear position operator, so not exact position operator, but the smear position operator. And there, a second parameter of the theory makes its appearance, is the smearing scale, which is thought to be of something of that order. The parameter lambda must be small enough not to conflict with precision tests of quantum mechanics, but big enough to explain the localization of macroscopic objects. The parameter suggested is, or the order of magnitude suggested for the parameter lambda is 10 to the minus 16, but this is not engraved in stone. You can be made in minus 15, minus 16, minus 17. Okay, so that's the general order of magnitude of the problem. So, as I said, the theory has been tested in the laboratory, and we must explore and use the theory in really very different realms from the realms that the theory has been designed to work with. We need to work with this theory in realms involving quantum fields and curved space-time. And as I said, we have to deal with many problems. One of them is the non-conservation of energy momentum tensor. And I will tell you how to deal with that, because initially it seems impossible to deal with that. Okay, so how do we deal with that? So I'll give you a brief description of what we have in mind as the formal way to deal with that. Although in the practice, we will, in the calculations that I will show you, most of them are using a shortcut. So I will not really use all these. Okay, the idea is to regard semi-classical gravity not as fundamental theory, as in some sense I already said, but as an approximate description with a limited range of applicability. And we will then take the view that during the collapse equations, the theory is not valid. Simply taking in as analogy, for instance, hydrodynamics and the Navier-Stokes equations. We know Navier-Stokes equations are very elegant equations. We know how to use them, how to solve them, but we know they don't describe reality at the fundamental level. So it's not surprising for us that situations arise in which the theory simply fails. You may describe a smooth wave moving through the ocean, but when the wave reaches the beach and breaks and produces foam and all sorts of things, the theory is not valid. Again, the foam dissipates and the smooth wave retreats from the beach back again. You may use again standard hydrodynamics. So we will see the collapse as something like that, as representing something like that. These fundamental degrees of freedom of which we know nothing somehow get excited during These collapses play a role there, and then they don't play a role again. So the idea is that in between collapses, the theory will, the description we will use is given in terms of what we call a self-consistent semi-classical configuration, which is basically, you know, a slight generalization of what you do when you do quantum field theory in curved spacetime. The idea is that you have a given classical spacetime. On that spacetime, you have a construction of a quantum field theory, meaning constructing the Hilbert space and the momentum and field operators. I'm thinking here classical scalar fields for simplicity. So you have the scalar field, the momentum conjugate, you construct those operators as operators acting on the Hilbert space. And in the Hilbert space, you choose a particular state that you will call the physical state, the only physical state. And that only physical state satisfies the following. The Einstein's equation, the Einstein tensor for the given spacetime metric equals the expectation value of the energy momentum tensor of that theory. Of course, I have to say here that this object is a very singular object, requires renormalization, and it's understood that this should be the renormalized thing. Note that this is it's kind of a generalization of the Schrödinger-Newton system, you know, and has the same type of self-referential aspect, because the quantum field theory is required to be constructed on the given spacetime, but the spacetime is connected to aspects of that quantum field theory, and in particular to this state which exists in that quantum field theory through this equation. So the two things are connected. So now let's imagine what happens when a collapse takes place. So if a collapse takes place and this state jumps from one state of the quantum field theory to another state of the same quantum field theory, this object will change, the expectation value will change, and therefore the spacetime metric will change. But if the spacetime metric changes, probably your quantum field theory construction needs to change. And then you cannot really do it. If you want to remain within this scheme, you need to have a full jump from one self-consistent semi-classical configuration to another. It needs to jump together. Once the state jump, there has to be a corresponding change in the spacetime metric. So if you want, we draw this in the blackboard, we imagine if we describe a single collapse, this I'm not going to say too much about this, but you imagine, you know, that you have a spacetime here with an SSC1, then your collapse theory is supposed to tell you, okay, on this hypersurface, a collapse occur, and that in that hypersurface, the theory gives you new data, and from that data you construct a second SSC, which has a whole new construction. And a succession of these things will describe your spacetime. Your Einstein equations would be valid in these regimes and will not be valid at these points. Okay. We have worked this out in detail. We have shown how it's done in some specific examples. Recently, we wrote a paper of how we think it can be done generically. It's highly non-trivial. Let me not get into that. And let me jump directly now to applications. So we will apply these general ideas to contexts where we find there's something else needed, where we have gravity, we have quantum mechanics, and we need something that we believe is not there.
One short question. This collapse is continuous?
Here is a individual collapse, but if you use continuous spontaneous localization, you would have a continuous collection of collapse, and then you imagine going through a situation which you have one collapse, more collapse, more collapse, and taking the limit. You want to imagine being able to take the limit. We haven't done this. It would require to be done. Okay, but yes.
The collapses will not be
So like you had the smearing which you introduced in the slide. So you expect like a small region around the hypersurface?
Yeah, it's not clear. It's not clear. Could be that it requires a small region. It may require small spatial region and need not be extended in time. We don't know yet. The construction we did is assuming that your theory, your collapse theory, tells you on which hypersurfaces the collapse takes place and which collapse actually took place. And what we did is then, if the theory gives you that on the hypersurface, how you construct the space-time and the state and the quantum field theory afterwards. But the assumption is that you had a collapse theory that gives you all that. Not that we do, but we constructed this scheme so that we could try it on different collapse versions of the collapse theory. Okay, but let's go and do something easier, which is applied to situations with high symmetry where we can certainly do many more things. So cosmology. Cosmology, as you know, contemporary cosmology takes inflation as one of its most attractive components. It basically corresponds to a very early stage of extremely rapid accelerated inflation, where the universe is described basically by a de Sitter phase, and this early stage is then turned off, and the acceleration turns off with double F here, sorry. And it's turned off at some point, so it's not simply de Sitter forever, but it lasts at least 60 or so E-folds, depending on which is your favorite theoretician on this field. Okay. Oh, no, doesn't work like that. Yeah. Okay, so the theory is described by Einstein's Hilbert action for gravity and a scalar field in the simplest way. There are, of course, many models that have more than one field and so forth. And then there is a potential, which, if the scalar field depends only on cosmological time and changes very slowly, this thing is basically a constant or almost a constant, and then it behaves like a cosmological constant. So the idea is that cosmological constant, very large value of this cosmological constant, will produce an accelerated, this accelerated expansion where all inhomogeneities and all defects and all anything that was there will become extremely dilute, and the universe will become homogeneous and isotropic to an extremely high extent. Such a high extent that I will say it is exactly homogeneous and isotropic to avoid having to say to a very right extent. Okay, so from now on, I will say it's 100% homogeneous and isotropic. Its biggest success is claimed to be its ability to account for the emergence of the seeds of cosmic structure as a result of quantum fluctuations and with the correct spectrum. And here we encounter this quantum fluctuations story playing a very fundamental role. And precisely that, the way that those quantum fluctuations are treated makes the story not theoretic, not conceptually satisfactory, despite the fact that the numbers come out conceptually satisfactory in a conceptual satisfactory way. So let me tell you how the analysis goes. The analysis goes by describing the space-time metric in fixing the gauge. This is a technical detail, and basically describing a cosmological model, Friedman-Robertson cosmological model in terms of this variable, which is called the conformal time. And the point is that we have a single variable controlling the size of the universe as a function of this time. And the only aspects of the metric that contains possible variations depending on location are this object called the Newtonian potential and this object that is represents the tensor modes or gravity waves. The idea, the treatment is to, sorry, and the inflation field is again taken to be a field that depends, has a value that depends only on cosmological time, on this time. And one adds perturbations that may depend on may contain spatial dependencies. The background is treated classically and assumed to be dominated by this inflaton potential that I said was very large. So the changes of field are the only changes of this field that are relevant are the changes of time, but they are supposed to be very slow. It's called the slow roll regime approximation. And therefore, one can see that the scale factor, the only aspect that is present, let's say present in the description, is the scale factor, and it behaves in this way. One fixes the convention so that and sets A equal to 1 today, and the value of this cosmological this time parameter takes only negative values from the initial time of inflation to the final time of inflation. Okay, that is all well and good. But then here we have the perturbations, the parts that contain spatial dependencies, which are the variations, these perturbations of the field and the perturbations of the metric are treated quantum mechanically and are assumed to be characterized by the vacuum state. Technically speaking, it's called the Bunch-Davies, or more precisely, the adiabatic vacuum. It's a state that is 100% homogeneous and isotropic. And the idea that this is the state that represents the physical situation is precisely because inflation dilutes everything that was present due to its fast and long acceleration. Okay, so the next thing we are told is that the state is also characterized by quantum fluctuations, and these quantum fluctuations are nothing but uncertainties in the quantum state, uncertainties in the field. And here we see an instance of the first confusion we noted. The usual treatments basically view and interpret these quantum uncertainties as if they were stochastic fluctuations. And then from looking at these quantum uncertainties as stochastic fluctuations, they claim to have an explanation for, or an account of, how the first inhomogeneities and isotropies arose, and those evolved eventually to form galaxies, clusters of galaxies, and so forth. But there is something very, very problematic about this picture, because the background universe was completely homogeneous and isotropic. The state of the quantum field is completely homogeneous and isotropic. In here, we are adopting a view in which the state, or the quantum state, is all there is to say about the matter. The gravitational sector is described by the classical. Well, you don't need to do that, but this problem is generic. The fact that you have both background and quantum part completely homogeneous and isotropic. And we end up with the situation that is not. How does that happen? If the dynamics of this closed system, which is the universe, does not break the symmetries. Okay, so I will not tell you about the many proposals that are there. If you ask a cosmology, you are going to get an answer. If you ask a different cosmology, you are going to get a different answer. So our approach allows us to deal with the problem. We are told, following our recipe, the scalar field must be treated using quantum field theory, that includes the zero mode of the inflaton field, which will be taken to be highly excited and sharply peaked around some value, probably a coherent state, while the space-dependent modes are all in the vacuum state. The yep.
Just to make sure what the problem is. In the inflationary story, if I understand correctly, you assume that the quantum state in which you compute fluctuations of the inhomogeneities is itself homogeneous. So the quantum fluctuations as operators carry a spatial.
Okay, sorry. This is a long question that requires a long discussion. So we will take short, how you call it, close questions now. We will take discussion questions at the end. It's okay.
With the classicalization of those fluctuations?
Right. Well, before the classicalization, the fact that the thing is remaining homogeneous and isotropic. But right, because classically, okay. Let me discuss this discussion later. Is that okay?
Yes, perfect.
Sorry, I was told to do this.
That's not
Okay, so the behavior of the system is now described by the Einstein equations, and one obtains if the zero mode of the inflaton field is in such state, one obtains essentially the same behavior and a slow roll behavior for the now expectation value of the zero mode of the inflaton, because it should be treated quantum mechanically according to our. Now let's concentrate on the modes that are different from zero, and we will rely on a practical procedure. We have check, considering the collapse of a single mode, that it produces the same results as the whole shebang that I explained before, okay? But here we need to collapse a very large, infinite number of modes. So this is... Okay, so basically what we have is the early stages of inflation are characterized by the vacuum mode, the vacuum state. In that state, these operators, the field and its momentum conjugate, looking at the Fourier components, are characterized by Gaussian wave functions. They are basically harmonic oscillators. So they have certain uncertainties, and they are centered at zero, like a normal harmonic oscillator in its ground state. Now, collapse will modify the quantum state, and therefore the expectation values of both of these operators. So this is very, very important. Assuming that collapse can be treated as occurring mode by mode, and using one adapted version of collapse theories, in this case, CSL theory, and exactly the theory I just described for you, but now applied to each mode of the collapse of the field. And realizing that what we have is one universe in which each mode would correspond to one particular realization of the stochastic fluctuation, okay? We are going to now examine what's the prediction from the theory. Let's first focus on the metric perturbations, which are, in fact, the things that we are supposed to see in the CMB directly, the measure of the Newtonian potential on the CMB, and are supposed to be the seeds of structure. If I look at the Fourier decomposition of the semi-classical equation, the same equation that I wrote before, and I concentrate on the equation that for this perturbed metric, this particular variable, I end up with this equation. So it tells me that the Newtonian potential, the mode K of the Newtonian potential, is given by, well, this quantity, which was should have been the expectation value as well of the zero mode, and which was always different from zero, and then the momentum conjugate, the expectation value of the momentum conjugate of the field. But the momentum conjugate in the vacuum would be zero. So this would be zero, and the Newtonian potential is zero. And if that happens for all modes, we have a universe that is homogeneous and isotropic. When this guy jumps to a different state, it acquires an expectation value. Then this quantity acquires a value. and we are not longer in a universe that is homogeneous and isotropic. Okay, so here the equation clearly shows us how the symmetry of the space-time metric broke. Okay, now you have to do a lot of calculations. I will not bore you, just plug and compute and solve some equations. So the end point is that with reasonable choices, which is this I will explain to now, one can find agreement with observation. In particular, in the CSL version, we have explored the collapse either in the field operator or the momentum conjugate. Remember that the collapse operators play the role in the collapse dynamics, so you have to choose which one is the collapse operator. And in order to obtain actual agreement with observations, and also for dimensional reasons, one has to take the collapse parameter to depend on the mode in this way, depending on which collapse operator. That could be this replaced by saying that the operators that collapse are not the field and the momentum directly by this, but this particular modified collapse operators. The resulting prediction is a power spectrum that has this form, and if you are a cosmologist, you are used to this. This is the standard so-called scale invariant power spectrum. The magnitude is basically controlled by the size of the potential of the inflaton field. And here in our case, in the collapse theory, we get this multiplied by the collapse rate and the time of duration of inflation. If one takes standard grand unified theory values for the potential and standard time for duration of inflation, one can deduce from the magnitude of the spectrum what should be the size of this constant, and the number we obtain is 10 to the minus 19 seconds to the minus 1, which is not so far away from numbers that are being played with by, people, the proposers of collapse theories. Of course, this cannot be said that we are recovering that, because here we are collapsing in the field modes. There we are collapsing in the smear position operator. What is the relationship between the two is very, requires a lot of work, but it's still nice that if you get a number, it's not too bad that way. Other people have studied this, assuming different collapse operators, and depending on which collapse operators you do or do not get agreement with observation. So here is, in some sense, showing you that the theory is, that the situation is giving you information about what the theory should be if it's going to fit the data.
Just if the inflaton potential is in fact at higher energies, the lambda goes down.
Yep.
Right?
Yep. Yep, that would be the case. Yep. Yep, if you want the same. And if you don't change the time of the inflation. Yes. No, we couldn't. No. I said we shouldn't. Yeah. We should. I'm nevertheless not unhappy that the number doesn't come too far away, but no, we can't. Yeah, it's unfair in a sense. It's not. It's hopeful, but nothing more than that. Okay. Yes. Okay, but now let's go and do something else. So we have fit things so they produce the standard, the scalar modes prediction. Let's look at the tensor modes. Remember the metric, we had two things. We have this scalar perturbations, which are the Newtonian potential, and we had the tensor modes. There are other things that are not important because they are not to decay very quickly. So these are the two things that are relevant. For the scalar modes, again, Einstein's equation, semi-classical Einstein equation, exactly the same procedure, but now concentrating on this variable, gives me this expression, okay? And here, one point to note, well, first of all, the equation is a little bit more complicated on this side. That's not too big of a deal. But here, the first contribution comes quadratic in the part that is space-time dependent, the part that needs to undergo collapse. And that, well, then I can do the whole shebang, go to the Fourier decomposition and do the calculation and renormalize the energy momentum tensor and put everything there. And it turns out the expression is formally divergent, but there are good reasons to put the ultraviolet cutoff. At late times, we know that there is this silk damping. So things that oscillate very quickly will be damped. So we'll put this cutoff there. And then the prediction for the power spectrum of tensor perturbations is rather different than the standard, than the other quantity and than the standard prediction. The standard prediction is very similar to the prediction of the scalar modes. Actually, it differs only for this slow roll parameter called epsilon. That's the only change in the prediction. But our prediction is completely different. Note first of all that given that our source is quadratic in the thing, this thing turns out to be quadratic in the inflaton potential. Okay? The behavior as a function of k is different also. And the appearance of these parameters also appear quadratic. So the prediction is completely different from the standard prediction. So according to this analysis, you do not expect to see the tensor modes. In contrast with the standard analysis, which claims that the modes should have been seen, and it's creating a lot of problems for people in inflation to explain or to choose the few models that do not make this. There are a few models that do not, but they need to choose them. So let me compare here graphically the predictions that we made for the tensor modes with the standard one. This is the standard prediction for the tensor modes. It should have been, according to, for a simple potential like the one we have here, they should have been seen. So the type of potential that we use, this quadratic potential, in the standard treatment is ruled out. In our analysis, there is nothing to say. We're looking at modes in this regime from, let's say, 20 to 1,000. That's the regime we are looking. And we see that we are many orders of magnitude below the scheme. And that's the prediction using CSL theory, the blue one. And this is a prediction using a slightly contrived theory that we just used to check how robust our prediction is. So basically, this not exactly the same behavior, but basically the same general tendency of having a dramatically reduced spectrum that is less reduced at the very low, very low end, which is very difficult to see. Okay. How am I doing in time? I'm running out of time.
How much do you need? 5 minutes?
5 minutes.
Yeah, perfect.
5 minutes. So there is another problem that bothers inflationary cosmologies now, so much so that some of its most ardent proponents have become one of the most fervent detractors. So the argument for this problem, eternal inflation, is basically the propensity of inflation not to end, to last forever. And what's the argument? The argument is the following. Inflation is driven by the zero mode of the inflaton, which is slow rolling down the potential. But this mode is then is displacing classically, and we have a classical displacement in some natural time scale. And we should compare it with the quantum, they say, we should compare it with the quantum fluctuation of the mode and see which one is larger. if the quantum fluctuation, which is now identified as a stochastic fluctuation, is larger than the classical fluctuation, then the fluctuation can take the mode up or down the potential. If it takes it up, the value of the cosmological constant will increase, that region will grow faster, and more of the universe will grow faster, will overtake the other, will have larger values of the inflaton and larger values of the cosmological constant, and the inflation would continue forever, right? Basically, this is the diagram of the story. You compute the quantum fluctuations, compare them with the classical displacement. The quantum fluctuations could be in either direction, and if they are more important than the classical displacement, you get the problem. And it seems that in many models, in most models, you get the problem. Okay, but this argument, now that we have understood certain things, raises serious concerns. First of all, once again, we are confusing quantum uncertainties with stochastic fluctuations. And these are not the same thing. Stochastic quantum fluctuations by themselves will not indicate something is changing randomly in time or in space, nothing of that sort. Second of all, the inflaton is driven by the inflation is driven by the inflaton zero mode, which by definition is homogeneous and isotropic. So it can, whatever happens to this mode cannot make one region of the universe do something and another region of the universe do something else. So it seems that there is no solid argument for eternal inflation. However, as we have seen, we need to supplement the standard story with a collapse theory. And once we introduce collapse theory, now we have the stochastic aspect of collapse theory, and that can revive the eternal inflation problem. It will be now the stochastic fluctuation due to the stochastic aspect of the collapse theory what can move the inflaton up right? It's not the quantum uncertainties, but it's the actual stochastic fluctuations moving the state. So we need to compare these two again. If we look at the case in which the field is taken to be the collapse operator, the collapse rate goes like lambda times k. So k equals 0 should not collapse. So it seems that, okay, we are done. Unfortunately, no, we are not done, because modes that are extremely large, larger than the cosmological horizon, actually behave as if they were zero modes. So we have to look at the behavior of these modes and their contribution of these modes to this stochastic motion, right? For the sake of our universe, at practical levels, at the level of our universe, they would be as if they were zero modes, but they would be subject to collapse. Of course, so we have to compute this stochastic aspect, which is measured by the expectation value of the field subject to the CSL evolution computed over average over, all the realizations to see how likely this is. And we need to sum of all modes that have wavelengths between infinite and wavelengths that are just outside the particle horizon of the thing. And in fact, we will look at a slightly generalized type of decay rate for lambda parameter, which becomes proportional to k for k sufficiently large. For the case that we see in the CMB, these are the values of the case that are relevant. So this parameter better be much smaller than those numbers if we are not going to affect the observations. So this is a paper we just got accepted in this journal. It's going to appear very soon. And here is the parameter space where in the alpha B parameter space, where the eternal inflation problem is avoided. Here is a region in which we do have eternal inflation. But the point more than this particular graph is a generic lesson. By taking these issues at heart and examining them carefully, problems that seem insurmountable, now you have an opening but to solving this, right? So I'm not trying to advocate that this is the particular form of the thing, but the point is that there exists now solutions. Which one is the right one? I'm not trying to advocate that. Okay. Now let me say one final word about something completely different, because I talked about inflation and I talked about cosmology, and I wanted to focus on cosmology, but it's interesting to see that there is some other places where this approach is interesting. A black hole information problem. The black hole information problem, according to the analysis by Hawking, quantum effects, quantum field theory effects, cause a black hole to radiate. Therefore, it should lose mass and probably disappear, leaving perhaps just a small remnant, which is irrelevant, and most of the energy in the form of thermal radiation. And normally, one is told, well, quantum theory requires a unitary relationship between the initial and final state. The first comment is that this is true only if the state is a full state, and for that, the state better be on a Cauchy surface. And in this graph, this prevents anything here from being a Cauchy surface. So in reality, the problem only appears if quantum gravity resolves the singularity, removes the need to have a singularity, and restores global hyperbolicity to the picture. So if we assume that quantum gravity does that and removes the need to have this singularity there, and removes the need to put a boundary there on space-time, then we do have a problem. But we do have a problem only if quantum theory really requires a unitary relationship between initial and final states. Collapse theories do not require a unitary relationship between initial state and final state. Collapse is happening all the time and is erasing and creating new information, and then there is no need for the problem. We have done a little bit more than that in these papers. We have shown specific schemes where you can show how all the information that goes into the black hole under, again, certain assumptions can be erased due to the collapse dynamics. And well, this would require another talk. Okay. Yeah.
Collapse also is unitary, right? You normalize the state after.
I know, but it's not unitary in the sense that doesn't relate the state at the end by unitary people don't mean just the fact that the norm is preserved. It is the idea that you have a one-to-one mapping between initial states and final states. And in particular, given the final state, you can reconstruct the initial state. You can use unitary operator to evolve forward and backwards. And then the information in some sense is all contained equally at the end or at the present. And trying to accomplish that in the case of a black hole has been a big headache, right? So, but here we bypass the problem because we say, no, quantum theory doesn't require unitary evolution. By the way, probably if you give a talk to an audience filled with experimentalist physicists, they will tell you, wait, quantum mechanics does not require unitary relationship. We have reduction happening all the time in all our experiments, and it's not true that we have, but okay. So I'm almost done. So we have seen that consideration of conceptual aspects related to foundations of quantum theory can have substantial impact in inflationary cosmology and elsewhere, and sometimes modify the standard conclusions. It's not just, philosophical satisfaction that is provided by this approach. You can also modify the conclusions. We have seen that we need to add something to the standard story to really account for for the creation, the generation of the seeds of cosmic structure. We have seen that in this approach, we naturally generate a very different prediction for the generation of tensor modes, which are being looked upon by search of polarization B modes in the CMB and have become a source of frustration for many cosmologists. And similarly, we have show that we can change our view or on the seriousness of the problem of eternal inflation, how inescapable it is, which is normally considered as really catastrophic problem. We have seen that it need not be. Thank you very much. Now, yes, Daniel.
Maybe you can speak into this so that some people can hear.
Yeah. Well, I was just asking for some more clarification of what is the problem on the inflationary scenario side. So you have a homogeneous vacuum state for the fields. The fields themselves are not homogeneous. So
what do you mean the fields are not homogeneous? The fields don't have values.
I mean that you are quantizing the fluctuation fields, the perturbations over the homogeneous configurations. And so field operators are, in principle, have a spatial dependence.
The operators are depend on X.
The field operators.
Delta phi is delta phi of X.
Yeah, exactly.
Right.
And so, although vacuum expectation values indeed lose that dependence because they're vanishing, then the quantum fluctuations, so the higher order operators, will carry dependence on X.
Right. So take two spins. Okay, so this is the kind of question that So the question is whether quantum fluctuations, quantum correlations, quantum correlations like these objects, these objects imply or can be taken to indicate that something has broken the symmetry. The fact that these things are non-zero can be taken to this, right? That's the question. Let's see. Let's take another situation. Two spins, spin 1 and spin 2, particles or two particles, particle 1, particle 2, a spin system, and let's it be a singlet. Let's look at the projection of spin 1 in the direction n1, spin 2 in the direction of 2. That projection is proportional to the cosine of the angle. That's the standard Bell, which is basically the product of n1 and n2. Does that mean, can this be taken to mean that before a measurement has occurred, the singlet state is not longer rotationally invariant? No. This means that if you were to do a measurement and were to measure the spin of the system 1 and were to measure the spin of system 2, they are going to show statistically these correlations that go like that. But it does not mean that without a measurement, the state has lost its rotational invariance. And the same is true here. The fact that this is non-zero tells you that if you were to measure the field here and you were to measure the field there statistically in a large set, you will obtain this correlated value. But having had no measurement, the state is translationally invariant. So the existence of quantum correlations does nothing to remove the argument. Your situation, which is fully described by the state of the quantum field, because you don't have hidden variables. If you have hidden variables, of course, there is another story. But if you don't, then your full situation is fully symmetric, and you cannot account for the fact that we are seeing inhomogeneities and
isotopies. So let me understand if I understood. Let me check if I understood. So the statement is there are quantum fluctuations carrying a non-trivial spatial dependence, but this which is that quantity. I just mean that quantity has a non-trivial dependence on the spatial
on X and Y, yes.
on the other hand, this in itself does not imply that you're going to measure inhomogeneities.
That there will be inhomogeneity, that ontologically there will be inhomogeneities and anisotropies.
And then in particular, there is the other thing that I mentioned, that what you actually measure are classical inhomogeneities, and you would have to show also how those quantum
Well, I don't. That story I don't buy. You don't measure anything classical. There is nothing, absolutely nothing classical in the world. All the world is quantum mechanical. Classical may be our description. When certain quantum states have certain particular situations and under certain conditions, and if you are interested in measurements with certain properties, you may describe things classical, but things are never classical. Classicalization is not something that happens to a system. No system ever transmutes itself from being quantum to being classical, and in particular, if you do quantum gravity, believe also that gravity is quantum, and there is never classicalization. So the only thing about classicalization is that sometimes some states are suitable to a degree, certain degree of approximation, can be well described in classical terms. But look, the quantum description, as philosophers say, supervenes on the classical description. So there is no property that can be present in the classical description that is not already present in the quantum description. So if at the quantum level of the description, the thing is homogeneous, at the classical level, better be homogeneous. If not, you're not doing a good description.
Okay. So is there another question here? Dirk? Okay.
Okay.
So I would have two questions. The first question, already yesterday you spoke about this difference between stochastic and quantum fluctuations. Maybe in a very primitive system like harmonical oscillator, or maybe a scalar field.
Harmonic oscillator.
Yeah, but what is really the difference that you draw?
I want to emphasize. Okay, this is an excellent question. Can I put there, or should I erase this?
No, that's fine.
That's
over
fine.
there. Yeah.
Okay. Or it's wet.
The chalk is wet?
No, Okay, so let's look at an harmonic oscillator. Harmonic oscillator in its ground state. Okay. The harmonic oscillator in its ground state has a wave function by 0, x, with, if the potential was centered at 0, this is centered at 0, we take the 0 there. In particular, this wave function has the symmetry x goes to minus x.
Mm-hmm.
And we have a quantum uncertainty, right? Which is, right, basically the expectation value of x squared in that state minus this, that is 0, right? But this is 0. Square root. Mm-hmm. Right? That is what we call the quantum uncertainty on x. That is the quantum uncertainty. So some people call it the quantum fluctuation, but nothing is fluctuating. There is nothing moving in time. The state is stationary, right?
In Bohmian mechanics, you would even say, well, I mean, if,
okay, Bohmian mechanics would be another story, right?
But maybe my confusion comes exactly from that. Yeah.
Okay. Then go ahead.
No. I mean, I would just say, like, I mean, there I would use the typical interpretation of stochastic fluctuation. I mean, if I have many copies of the system, and I look at many copies, I have an expectation value.
You're right. In Bohmian mechanics, the quantum state is not the full description of the system. Mm-hmm. You have this extra variable, call them hidden or something. Mm-hmm. So your whole ontology is not meant to be described by the system. In standard quantum mechanics, it is. Mm-hmm. So in Bohmian mechanics, it's true, there would be another story. You could try to address, and people have this issue, using Bohmian mechanics, you know. There are people addressing this issue of emergence of structure using Bohmian mechanics. That's a viable, I mean, I don't know the details, but that's in principle a viable story, because clearly, despite the fact that your system, your wave function is symmetric, that's not all there is. There is more stuff to it, the Bohmian positions. And then, yes, in a collection of systems, you would have the positions realized in taking different values, and then you would have something that looks like stochastic fluctuations, not occurring in one system, but occurring in a large collection of systems, right? But that is Bohmian mechanics.
Granted, yeah, okay.
This is not Bohmian mechanics.
Okay, then I understand what you mean by these quantum fluctuations, but what is then the stochastic fluctuation?
So at this point, there is absolutely nothing stochastic.
Okay.
How do you get something stochastic here? You do a measurement. In standard mechanics, you do a measurement. You go and measure the position X with a more precision than this width.
I see.
And you obtain this value with this precision. And the state now is this.
Okay,
the state is not longer the ground state of the harmonic oscillator. In fact, to change the state from here to here, you have to inject energy.
Okay, I understand.
This will not, in standard quantum mechanics, this will not happen absent somebody that comes from outside and makes a measurement. And if you repeat the measurement, you prepare 1 million copies of this harmonic oscillator, prepare them all in this same state, and make 1 million, measurements, you will obtain, a large number of results that you may describe in terms of a stochastic variable.
I understand. So it's in terms of measurement, yeah. Okay.
But in the early universe, there is nobody making a measurement. Then you cannot appeal to this part of the story.
Absolutely agree. Yeah. Okay. And the second question, if I still may, I'm looking on the participant list, but there's no hands raised at the moment, so I'll ask a second question. When you say, I think at some point you said a collapse occurs, and then somehow you have to rebuild, I guess, the Hilbert space, your field operators, or let me say, you've probably to choose a certain representation, like in which you somehow represent your states in the Hilbert space. Is it that clear really what the vacuum at let's say Hilbert space, initial Hilbert space, and then after the collapse, the final Hilbert space is, or is there any
well, we have invented, you see, we have to invent some recipe to glue the two descriptions, okay? So we have invented recipes, okay? The recipe that we have tested a lot this is more than wet, it's now.
Yeah, better you take a new chalk there, yeah. Or
take
one over there.
Chalk and perhaps take a new blackboard. So the recipe we have taken is to say, here we have a space-time metric and a field operator and the state, okay? So we have considered various recipes. The first thing that we have to give is you need to give some geometric data on this hypersurface. So let's call this G1. This metric induces on this hypersurface a metric, a tree metric, which we call H1. And we demand by hand that the metric induced here, the metric 2, induces the same metric. So HAB2 is equal HAB1 on X for all X in the collapse hypersurface. Okay? We cannot ask at the same time, the second set of geometric data is called the extrinsic curvature, that is basically related to the time or the normal derivative of this thing. Okay, you cannot demand this. This cannot be demanded. Okay. So now you have to invent a recipe for what you are going to do this. But one thing you want to do is you want the new data to satisfy the so-called constraint equations. And those are 4 equations that 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 will be used to limit this thing. The second thing that we want is that the expectation value in the collapse state. You see this? My theory told me to collapse the state to a new state. So a very natural thing to ask seems to be that the new state that I will have here, the new physical state of the second construction, will have an energy momentum tensor that on the hypersurface is the same as the first state energy momentum tensor. This is of the first construction. This is of the second construction.
Mm-hmm.
For all x on that hypersurface. Okay? Mm-hmm. So those are requirements that seem natural to us. If my collapse theory was telling me that I should collapse to this state, which now I can't because it's not longer in the, I will have the second state of the second construction be required to do this, right? These things are general. This thing will, in interesting cases, would be different from zero. So it's not going to be the vacuum, or it's, in these cases, it's going to be space-time dependent. You will collapse, for instance, from an homogeneous anisotropic situation to one that is not. So this thing will be non-homogeneous and not isotropic. It will be dependent on space-time. Okay, so
okay. Okay, thanks.
These are questions these are questions that need exploration. We are still in the exploration stage of how to control these things. Actually, very difficult questions arise here because these things, as I mentioned, need to be renormalized. And that's a whole mess. It's really a terrible mess.
I guess also like the fog representation before and after the collapse has to be matched in some way.
Well, we are not demanding that because it seems unclear why we should demand that, but that would make things easier. But let's not demand more than we need at the moment.
Yeah, so there are two questions by the Zoom audience. Yeah. So Tim, please go ahead.
Okay, can you hear me?
Yes.
Okay. Hi, Daniel.
Hi.
So I just want to ask a kind of question from very, very far away from the details, which is just about how you think about, and when I'm just thinking about how you're solving this problem of breaking the symmetries through the collapses. Clearly, at some level, it's by your choice of a collapse operator, right? I mean, essentially, you're putting in at some point in this recipe, as it were, I mean, it almost seems teleological when you talk about it. It's like, this is where the collapses are trying to drive you, right? They're trying to get you close to some state. Well, and I mean, you don't have to put it that way, but I think actually those words, something like those words may have come out of your mouth spontaneously.
They did.
No, and so at a kind of very high conceptual level, where say in a Bohmian approach, there just are no collapses fundamentally, but you can somehow derive analytically effective collapses of various sorts, depending if you define a conditional wave function or whatever. But the point is there, you just have no choice. I mean, all the fundamental dynamics is Schrodinger and whatever the guidance equation is. But it looks like in this approach, you've got this new degree of freedom, right? I mean, somewhere I'm gonna pull a collapse operator out and stick it into my dynamics.
Yep.
And so one might think that's a tremendous amount of freedom.
Yep.
And given any single particular problem, you might think, well, probably I can find some operator that'll do what I want it to do.
Yep.
by kind of reconstruction once I figure out what I want it to do.
Yep.
But you might think, yeah, that's a kind of virtue, but it's also kind of a vice, right? Because it looks not so principled, right? It's just driven by matching whatever problem you happen to want to solve at the moment. Whereas it at least kind of conceptually seems better, where the fundamental dynamic seems more intrinsically motivated or more intrinsically constrained. So, I mean, what's your feeling about that, and about the particular collapse operators that you're appealing to here? Do you feel like they have some independent thing to motivate them, or are you kind of just motivating them through the phenomenology of these particular problems?
Okay, yeah. First of all, you are 100% correct. These words, in fact, came out of my mind. I now regret it. They were meant to be descriptive of how the theory is written, or how the theory will, for instance, work if we turn off the Hamiltonian dynamics, what the theory would do. And that's what I meant when I said this is what the theory wants to drive things through. But your other point, that I am at this point choosing the collapse operators that do work, you're absolutely right. But what I see us as doing is exploring different regimes in which we will discover which kind of operators work in those regimes, and then try to look at multiple regimes, look at laboratory experiments, cosmology, black holes, and try to find one single operator that will reduce to all the corresponding operators in the appropriate location. You are completely right in the sense that we would like a theory, a fundamental theory, to have one operator once and for all. And it should be the same operator, could be more abstract or less abstract, but it should be the same type of, the same operator with the same constants and the same functional dependencies in all theories, right?
Yeah.
So it should reduce, for instance, to something like smear position operator in non-relativistic quantum mechanics. It should reduce to something that produces the right spectrum in cosmology. It should reduce to something that erases information sufficiently fast in the black hole information, and so forth. It's like trying to get clues from different regimes to what is death theory. But if the aim was for each particular theory just find which thing works, I think you're right in being very critical of that approach, because that couldn't be, couldn't be a reasonable theory. I see us exploring regimes of questions that have not been explored, and in some sense, not very different from the situation in which, let's say, particle physics found itself in the early 40s, where you had, large collections of particles. Nobody understood the zoo of particles that were coming around and were inventing things here, right? Isospin and strangeness and blah, 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 until eventually people were able to put everything together in the standard model in a unified language. So we at this point are in the exploring mode of trying to see what works in these regimes. And of course, a very important question would be to try to enlarge and see how large is the set of things that give me a correct, an acceptable answer for inflation, both for the tensor modes and the scalar modes, which are the data that I have at this point, right? But a very urgent question, which I recognize I don't know how to handle and face at this moment, is now construct an operator that does that and reduces to something like smear position operator in non-relativistic regime. You asked me to do that, I don't know how to do it.
Sorry, why doesn't
Thanks.
the operator leave the same level as Hamiltonian? why can't you have, for different systems, just like you have to understand what is the correct Hamiltonian,
Right,
you
right,
also
right.
have to understand what is the correct
Right,
collapse
but you
operator.
expect if let's say we are talking about particle physics, you know that the correct Hamiltonian is the Hamiltonian of the standard model of particle physics, and
Sure.
that you would put the whole Hamiltonian and then say, oh well, but this problem QCD doesn't, the strong interaction is not playing a role, so I can throw this out, and I can throw these other terms out because this other thing is not present, and then starting from the full Hamiltonian of your unified theory, which is the standard model of particle physics, you will find what are the relevant terms of your full Hamiltonian, which is a unique one Hamiltonian, good for everything, in principle. In principle, in practice, of course, if you are going to construct a building, you're not going to start with the standard model. But you know that in principle, you could have started from the standard model, or you believe you could have started and compute the Hamiltonian of this chair, right? You believe that because I mean, to the extent that we believe that the standard model is the fundamental description of the particle world that
I just want to say it's not a matter of principle. It's just that in principle, there are different descriptions, different models, which include different Hamiltonians and may include also different collapse operators for different systems. Then, of course, the more we manage to unify, and have a single description that covers many systems, the happier we are.
But you expect
how much you can push that, I don't know.
I mean, you're right that here I'm pushing unification. I would hope that we can, write a collapse theory that is at least applicable in as a unified way as the physics we're working with.
But let's. But should we have what's question first? Okay.
Okay.
Okay, then sit down.
Do you have an example in mind of empirically adequate physics descriptions which worked with different Hamiltonians and were not derived from a common but bigger Hamiltonian? No, because I thought you were saying we have
specific Hamiltonian for specific systems starting from, I don't know, grand unified theory Hamiltonian.
No, I was saying you said there are different Hamiltonians, different descriptions. So do you have some physics example in mind?
Where different Hamiltonians for different systems.
Yeah, what he has in mind is, imagine you write the Hamiltonian for the Ising model and you write the Hamiltonian for the hydrogen atom. These are two different Hamiltonians, right?
For a scalar field theory. Different systems, different Hamiltonians. Then, in a certain sense,
they all come from.
Them can be derived with some bridge laws, some approximations,
right,
from a single description. Some of them,
but
do that.
We don't. Some people do, right?
And if you think that is possible in principle, is an article of faith.
But the goal is still to start from the, let's say, n electron, m nuclei Hamiltonian, which is chosen and fixed for all.
I'm just raising the possibility that the collapse operator has more or less the same status as the Hamiltonian. For different systems, you have a priori different ones. In many cases, you can probably unify. Ideally, you can hope for unifying completely, having a single operator from which you derive all the others. Fine, but same status. I'm just objecting to the idea that the collapse operator has to be somehow unique, and then Hamiltonians could be different in different cases.
No, I agree, but in the sense we are looking for a theory, unified description of nature, and we have managed to move along in that direction quite a bit, right? We have now unified basically the three forces and have gravity trying to follow along, and to that extent, we should, if we are saying, okay, this is the fundamental theory, it should be on that same level. But in practice, given that we, for instance, the standard model does not contain the inflaton field, right? So it's not. It's not
necessarily that you don't have to adapt the collapse operator to the situation, but the question is the degree to which you have to fine-tune it.
if you really have to pick up the detailed features of the collapse operator to match the detailed feature of the CMB spectrum, then you have a problem.
Yeah, I agree.
If you just have to choose a collapse operator to match the CMB spectrum that is different from some other cases, maybe that's okay. I mean, there's no, in itself, I wouldn't see a problem. For me, it's more of a matter of degree of
okay, but
fixing the
even the
details.
issue of degree, you have to take it, because you could say the fact that you have to fine-tune the elements of the Kobayashi-Maskawa matrix to whatever numbers come in the, well, you have to fine-tune something. Sometimes numbers need to be fine-tuned. And that's it.
Okay, so let's have now the question by what? What?
Okay, hi. Yeah, so Tim mentioned this ambiguity about the collapse operator, right? So my question is similar. Also, when you do the semi-classical theory, choices have to be made, right? How exactly do I get an energy momentum tensor from my quantum system? Okay, and I suppose also many choices are possible there. And is there a natural choice, or is there some robustness if you have different choices? And like related to that,
well,
suppose you did something similar, like what you did now for gravity. Suppose you did something similar for electrodynamics. Is there some like quantum system, fully quantum system, that you could reasonably approximate with this kind of approximation, or not?
Well, you hope, for instance, that there would be situations in quantum electrodynamics where, for instance, you may treat the electromagnetic field as almost classical and try a semi-classical description and keep the electron field as quantized, and then, well, then try to see what is a reasonable characterization of this classical description, which from the beginning is only meant to be an approximation, right? I started by saying that this thing, I view them as approximations. And of course, yeah, approximations. One thing about approximations is that they need not be unique. You can have multiple types of approximations, some better in some conditions, some better in other conditions. After all, they're approximations. We believe, or we have the tendency to think, that if there is a fundamental theory, it is in some sense unique, or unique up to diffeomorphisms or something like that, right? But approximations don't have that status.
Right. And if you start from a fundamental theory, you can see under which conditions these approximations are valid, right? So now you have to guess.
If you start with a fundamental theory, you have a great advantage. But here the problem is that we don't have a fundamental theory to start with.
Right. So how can you have any trust in your approximation? And because you start from guessing an approximation, then you hope that...
I'm guessing, I'm making an educated guess. I know that classical GR works very well in a very large number of situations. So I want something that seems easy to become, to transform into the classical description of things. You are imagining how, nevertheless, we put the energy momentum tensor of a star, and we define it in terms of a fluid or something like that. But of course, there is no fluid, and there are, very complicated things happening, and your energy momentum tensor, you're trying to.
Yeah, in a sense. So there you don't make any further choice than to say gravity is classical, but just like the detail of the implementation. Because I thought I heard you say, I assume continuity of the 3 metric.
Okay.
And the momentum can jump.
This implementation,
but for example,
this implementation, you're 100% right. This implementation is the simplest one we could think of. So you start with
also do it the other way around, I suppose. Make the conjugate momentum continuous and then the metric jump.
I mean, here the inspiration is something very simple. When you imagine describing hitting a ball with your foot, right? At the first order description, or the 0 order description, you would say that the velocity changes dramatically instantaneously because you just hit the ball, but the position changes continuously, even if not differentiably. So you know, of course, that the velocity doesn't change instantaneously, that in the end, the ball deforms when you hit it and starts accelerating slowly by the combination of the external and internal forces and all sorts of complicated things. But to a zero-order approximation is very natural to say, well, the thing that undergoes the jump is the time derivative, the higher time derivative of appearing in your equation undergoes a jump, and the other thing just changes continuously. This is what led us to choose continuity on the metric and not on the other thing. But this, again, the simplest thing we could guess.
Okay, I understand that. Thanks.
You're welcome.
Okay. So thank you. So thank you again for this talk. So Dirk, you want to announce something for next time, or?
Yeah, I think, yeah.
Let's do that.
So thank you all for coming. Next time we have Anirudh Gundi from Trieste, who will also continue to talk about decoherence and the quantum vacuum. Yeah, see you all next. Would be a pleasure to have your faces again in the round. And
okay.
Thank you to the speaker again.
Thank you.
Bye-bye.
Bye-bye.
Yeah. So it was great.
It was great seeing you. Okay, let's keep in touch.
Yeah.
Let me know when you land in the